My name is Joseph Eidzork. I am the Director of Product Management for all the non-relational databases at AWS, inclusive of DynamoDB. Joining me today is Amrit Kumar, is Senior Principal Engineer on DynamoDB. And Amrit is one of those people I'm sure you all work with, but for me, is just one of those people that makes every day better for me, either through feedback, I learn from him, it makes me laugh, gives me feedback. It's a pleasure to be sharing the stage with him today. We're really excited about the content we're going to be sharing. We're going to take a look at some of the architectural choices that we've made with DynamoDB in the past and we continue to make to serve our customers. I'm going to try to give a little bit more of the explanation of the why and some of the how of some of the things that we do and continue to do to give you a better idea of how to use DynamoDB, how to think about DynamoDB, and to learn from some of the challenges that we've had. So we look at the customers in this screen, and we look at, technology-wise, or, what do all these customers have in common? Or what do these companies have in common? Well, they all have high-throughput applications that do the same thing over and over and over and over and over and over and over again. Put an item in a shopping cart, get the location of a taxi cab, start a session state, credit something, get a gaming player state. These are not complicated queries. They want to do the same thing over and over and over and over again, and they all use DynamoDB for that. So we're going to talk about some of the architectural choices on how we achieve any scale, high availability, and really consistent performance at scale, thinking about how we reduce variance. So one of the mental models I want you to think about DynamoDB as we kind of go through this is DynamoDB is really an optimization. When we set off to build DynamoDB, we didn't think about it as like, can we make a slightly better relational database? Right? We really wanted to build something that was significantly better on the dimensions of scalability, of consistent performance, of high availability. We'll talk about some of those aspects. So kind of in Amazon fashion, who is the customer? What we're actually working backwards from, and who do we continue to work backwards from when we think about the choices we make and what we're really trying to build? So it all started as actually about to the week, 20 years ago. If you can imagine, you're doing your holiday shopping right now and you go to the Amazon.com website and it's down for many hours. Happened 20 years ago. That's not a good thing for an online retailer. So what happens at Amazon when we have such a, I would say, a massive failure like this, is we go off and we write what is called a correction of error document, a COE. And what a COE really does is, from a technical perspective, really look at what went wrong. We go through the 5 whys, we look for root cause, and we start to think about what are the remediation actions from this. And one of the really more interesting things that we learned from this COE was the way that we were using a relational database 20 years ago. 70% of the access patterns that we had in this relational database, accessing a single key in a single table. 20% were just accessing multiple keys within a single table. 90% of what we were actually doing on the database had nothing to do with any of the relational capabilities that relational databases afford. So a few people, Swami and Werner, who you've probably seen speak this week, really questions, why are we using a relational database for this workload? We're just doing the same thing over and over and over and over and over and over again. Why do we need a query processor? Why do we need heuristics? Why do we need statistics? Why do we need a query planner? And they went off and they wrote this paper called the Dynamo paper. And they actually ran the system in production for multiple years before they actually wrote the paper so they could speak from experience. And what the DynamoDB paper really was our first foray into NoSQL databases at Amazon. And it was good, but it had some downsides. It was still a self-managed thing that was only available to Amazon internal teams. So over the years, we continued to use the Dynamo. And I just want to say for the record, Dynamo and DynamoDB are two totally distinct, separate things. Yes, they're both non-relational databases. Yes, they're both distributed databases, two totally separate things. But we continued to use DynamoDB, and we started to talk to external customers. We had a bunch of external customers that were doing sharded architectures on top of MySQL that had same things. They're doing the same access patterns, just using primary key lookups. And they're going through a lot of work to maintain these sharded applications, especially as kind of the cloud and some more scalable applications were ramping up. So in 2012, we launched DynamoDB. We've been running this, it'll be 13 years in January, and we've learned a lot over the years, and we continue to learn about what we want to do moving forward. And while we do a lot of innovation in the stuff that you see in What's New posts and blogs and all the kind of the customer-facing stuff, we do a whole bunch of stuff under the scenes to continue to think about scale, high availability, reliance, consistent performance that we're going to share with you today that's a little bit different than the stuff that we do. We're going to talk about some of the choices that actually enable a couple of these features as well. So over the years, and we get this a lot, is what customers come to DynamoDB. Externally, we have 1 million customers that use DynamoDB, which is just humbling from the perspective of where it started and where it is now. We see two major groups of customers come to DynamoDB. You have the customers that come to us and say, hey, we've exceeded what our current capabilities have on our existing database, or we're going to build an application that we just know just needs to scale from day one. We know we're going to have 100 million customers. We know we need a database that's at scale. For DynamoDB, we have hundreds of tables over 200 terabytes. We have hundreds of tables that do over 1 billion requests per hour. We have hundreds of tables that do more than 500,000 requests per second. And then we have a category of customers that come to us and say, yeah, maybe we'll grow that big one day. But you know what we really like about DynamoDB? No ops. Right? Don't have to provision infrastructure. I don't have to do versions. I don't have to manage hardware. I barely even have to think about capacity. And we see a lot of use in that one as well. So if we're really thinking about, let's go with the big use case for this one. If we're really thinking about, if that's kind of what we're working backwards from, and that's kind of, the scale of applications, what kind of architecture do we need to build to be able to afford those capabilities? Well, if you can think about DynamoDB really as a distributed hash tail, right? Like if you think about that as a mental model, you can think about it really as, how do we provide something that provides nearly unlimited scale, but also consistent performance? And for that, we have to think about DynamoDB as an optimization, right? We have to make trade-offs to achieve those objectives, and some of those trade-offs we've had to make are in the form of, the surface area that we provide from an API perspective to be able to trade off to be able to provide these things. As a distributed system, the second you take the data out of a single image system where you have shared processors, shared memory, whatever, shared disk, this is why data modeling matters for distributed systems. It's not unique to DynamoDB, but it's unique to anything that takes data and distributes it across one or more or two or more machines. You need to think about the data model and how you place that data. And this is why when you go to reInvent, you see quite a few data modeling sessions for DynamoDB. Alex Debris is masterful at this. He's a wonderful speaker. But this is kind of why Alex, in his talks and his books, are so valuable, because as a distributed system, you have to think about how you access your data and where that data is distributed. So for DynamoDB, to be able to achieve this, we partition data. We're going to use this little green icon here to be able to kind of denote what a partition is. You can think of a partition as a unit of compute, right? It has some reads, some writes, in some storage. And we've placed the items that you have in your table, one or more items in one or more partitions. Very simplistically, you have a table, you have a partition key. That partition key goes through an internal hash function that we have, and we use that hash function to determine where that partition lies within the server. And we think about, how do we start to scale a database, right? Let's very simplistic scenario. Let's just consider we have a table that has one partition and has a key range between 0 and 9. Real life, much more complicated than that, but for illustrative purposes, right? You drive traffic to that, or you increase, let's say you use an on-demand table, you drive traffic to that. What we'll do to be able to accommodate additional scale is we'll eventually split that partition. We'll split that key space, put half the key space for simplistic purposes on one partition, we'll put the other on another partition, and off to the races. Say you continue to drive more traffic. We'll split that as well. Let's say you continue to drive traffic to keys 3 and 4. We'll actually go so far as be able to partition or be able to scale out the items in your database all to the point where you can actually have a single primary key on an individual partition. And that's a very key design point from DynamoDB. We built it to be partitionable, sharding, whatever which word you want to use, all the way down to the infinitesimal smallest item that we have within the database from the beginning. It's not a bolt-on on the end, or it's not something that we thought about afterwards. This was a core design principle that we built into DynamoDB. Okay? So if we have that architecture, well, what kind of access patterns does this afford us? Well, as a hash table, a distributed hash table, primary key lookups are really fast. Big O of 1, pretty straightforward. It's a pretty good access pattern for that data model. That's why it's so attractive. DynamoDB has the concept of a range key beyond the purpose of this talk, but for partitioning a range key, combination that allows us to be able to do, so given a partition key and maybe you have order date or maybe you have a monotomically increasing number, you can do range scans within that partition key. Of course, if you have those two things, you can also do the fun table scan thing as well. Where have we seen this before? Well, partition key lookups or primary key lookups, 70% of use cases we're working backwards from. Range scans are the other 20%. This is exactly what we're working backwards, and this is exactly the architecture that we picked to be able to satisfy our own internal Amazon.com use cases. Turns out, highly applicable to people outside of Amazon as well. As we look at the overall architecture of DynamoDB, every single aspect we have to think about has to be able to scale and horizontally, has to be able to scale horizontally from every single component. We can't have a single component within the service that becomes a bottleneck for one of the other layers behind it. We think a lot about this, whether it's a transaction manager, or whether it's PIDR, or whether it's the request router, or the load balancers. Every aspect of the system has to be able to have that near infinite scalability component built in from the very start. But since we're talking about partitioning, let's talk about storage nodes. So within a given storage node, and I hate to break it to you, but really the magic of serverless is there's a whole bunch of servers behind the scenes, and we do all the hard work to abstract it from you, so you really don't have to care about that. But I promise you there are many, 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 many servers, and that's really all it is just servers. But logically, you would think about, okay, we have DynamoDB has a whole bunch of storage nodes, and you'd say, okay, well, I have a table that has a whole bunch of partitions, and they all reside on a given storage node. That would be the case if we had a single tenant system. But one of the really key things in DynamoDB is it's really a multi-tenant system, and that really allows us to manage capacity and be able to do it at scale, hopefully very efficiently, to be able to afford capabilities to you folks as developers that it's really hard to achieve yourself as a single tenant system, right? So we look at a distribution of data, and we look at a storage node. There might be a storage node, and you might have one partition on that storage node for your table. But on that storage node, there might be a whole bunch of other partitions, right? There's going to be a whole bunch of other partitions. And really, serverless and with DynamoDB is the illusion that you don't, that those are dedicated resources to you, and we do a whole bunch of work on the resource governance of these servers to provide that isolation and to provide those performance guarantees. But the thing I think, and this is one of the new capabilities, and what this really affords us to do, is if you look across all the partitions that support your table, the accumulation of the throughput for each of those different partitions really tells you what that table is capable of doing, right? So you look at the sum of those, and this is a concept which has been around for a while, and like if you're really savvy with DynamoDB, you kind of can back your way into this, and you can kind of know it, or you've talked to us, and we've talked to you about it. But this is a concept that we recently had launched a couple of weeks ago, which we're calling warm throughput. And this is really what the table is capable of doing. This is really the partitions behind the scenes that are capable of supporting the traffic that you have. And for illustrative purposes, and why I think this is really important, a key aspect of why a multi-tenant architecture, why the scale-out architecture, and why the way we do this matters to you as customers and as developers, is illustrated on this graph. So let's say you have an on-demand table, right? And we're going along, and the orange line on the top, that is the warm throughput. This is what your table is capable of doing. As you continue to drive traffic to DynamoDB, we'll continue to split out partitions to be able to add more resources to be able to accommodate your workload, and you'll scale up what effectively the warm throughput is for that table. And then as your traffic subsides, that warm throughput stays there. And your traffic goes down, it goes down. It could go to 0 for a while, but that warm throughput is still there. So you get the illusion, really, of having a dedicated resources, and especially with on-demand, is you only pay for 100% utilized. You only pay for the requests you make, but you get the illusion that you have a whole bunch of resources sitting around such that if your workload spikes up again, you don't have to go through the splits again. You don't have to go through the scales again. That resource is there. So this is really what a distributed multi-tenant architecture really affords to be able to do these for our customers. So with that, I'll hand you off to my good friend Amrit. Yep.
All right. Everybody able to hear me, or somebody say yes or no? Yes? Okay, cool. Thank you, Joe. It's fun doing this talk because one of the things I love doing One of the things I love about my job is working with you who are our customers and understanding the problems you're trying to solve and how we can help you with that. How many of you have customers who are happy with your application being down for maintenance at any point in time? Raise your hand if you think your customers are happy with maintenance and downtime. I can't see too well, but nobody raised their hands. I believe that we need to build systems which have absolutely no downtime. Your customers want that. In order for you to do that, you need a database which can do the same thing for you. I've been in DynamoDB now for a little over 4 years, less than 5 years. In this period of time, the total number of planned maintenance outages we've had, 0. If you've used DynamoDB for any amount of time, tell me how many times you got an email saying that there's going to be an upgrade in DynamoDB, therefore you're going to have downtime. Anyone? No. We spent a lot of time building DynamoDB to be able to do this, and we're really happy we're able to do this. Now, of course, Murphy is around and well, so we will do that too. The reason for that is very simple. If databases require maintenance, it means your applications do not have availability. Very simple. I've been in around databases for 35-something years. Nobody likes downtime, and it's hard to engineer a highly available system. You cannot bolt on availability after the fact. So the reason why we want to do these kinds of talks is tell you what we learned when we built highly available systems, because we know that you want to do the same things as well. So I am positive that each and every one of us is going to make mistakes when we design systems. Please don't make the same mistakes we made. Make your own mistakes. And then tell us about them, tell everybody about them so we can all learn, okay? So the rest of this talk is structured in the form of some rules and some examples, okay? So Joe talked about the scale at which DynamoDB operates. Hundreds of customers who drive in excess of 500,000 requests per second. By the way, this is not including, Amazon. Hundreds of customers driving in excess of 500,000 requests per second. And one of the things, and of course, since we're in Vegas, this is perfectly appropriate. If you have a fair and unbiased coin and you flip it 50 times, how many times is it going to come down heads? Well, 25 times. The expected value is the total number times the probability. So if you have an engineer who comes to you and says, I built this code, I tested it, it only fails once in a billion times. It only fails once in a billion transactions. Would you accept that code? Use this. In our case, once in a billion times means this thing is going to fail many times in a day. Absolutely no way. Work to engineer your system such that it has no failures, because at scale, anything which can fail will fail. This is the statistical part of it. The reality is it will fail at the most inconvenient time. At the time when you don't want to get paged, your pager will go off, which is now why my pager is going to go off. No. Engineer your system so it doesn't fail. The way in which we do these things, here, let me give you an example. Everybody here probably has heard about DynamoDB global tables. Here's a global table depiction with a table in 4 regions. You do a write to any region. This is active-active. DynamoDB global tables are active-active. Yesterday we announced active-active synchronous global tables. Do a write in one region, it's synchronously updated to the other regions. So how do we go about doing it? Now, on the top, you have a replicator, 1, singleton. A write in US East 1 goes to the replicator, goes to AP East 1. A write in US East 2 goes to the other 3 through the same replicator. Okay? Here's another architecture. Every combination of regions in one direction you have a replicator. These are two choices. So we thought about this one, and we thought about this one. Clearly, this one's going to be cheaper, right? You have one replicator, runs on one host, easy. Here, I got 3 replicators, 1 in each direction. So if you do a write in US East 2, there's a different replicator not shown on this picture, which is going to get data to US East 1. 4 regions, 12 replicators. 1 replicator. Which do you think is a more available system? The second one. This is the way we built global tables replication. For every pairwise combination of source and destination, you have a single replicator. Why? The network link between US East 1 and US East 2 may be seeing a little bit of lag. Do you want the replicator doing that replication to also halt replication to the other regions? No. You want to confine the failure domain to the one link which is giving you trouble. If you did this, it's possible that the other regions would be impacted. You want to build a highly scalable system. You want to engineer it for high availability. Start thinking about what can fail. When it fails, because it is definitely going to fail, what is the minimum damage which it can do? Have multiple replicators. This is the way in which we start to think. And so when somebody joins the team newly as an engineer, we start teaching them things like this. I'll give you another example. This is so I told you I worked with databases for 30-something years. I came to Amazon, and they had a name for something which I had long expected to exist. So when you build a system, build it to do constant work. Operate a system at a steady load wherever possible. The reason for this is when a system is running at a steady load in all possible conditions, when something untoward happens, it just keeps going. Okay? So think about a system with a cache. Okay, you have a client, there's a cache bundled with the client, and there's a database. Now, caches are really good things. If your cache is warm and you're able to hit your cache 99% of the time, when your client makes a request, only 1% of the traffic goes to the database, right? That's the cache. Fast response, lower load on the database. All right. Here's a quiz. Take a second, read it. Same client, same cache, database. Your client is driving a traffic of, what does it say, 2 billion requests per second. Your cache hit rate is 4 nines. How would you engineer this database? So I'll give you a hint. It's not none of the above. Okay? Beyond that, I'm not going to give you any hints. So let's start from the bottom. How many of you think D is the right answer? Raise your hands if you think D is the right answer. Anyone? Okay. How about C? Anyone? Is there anybody in the room? I can't see any hands. Anybody for B? Okay, I see a couple of hands for B. Anybody for A? All right. You guys should be at some other talk. You know the right answers. That's the correct answer. Engineer your system for constant work. Assume that the cache has failed. The reason you do that is because sometimes the cache might fail. In a distributed system driving 2 billion RPS, imagine that you engineer your system so you can only deal with a 99.99% cache hit rate. Let's assume you do a software deployment on whatever is hosting the cache and you take out 1% of the cache. Next thing, your database fell down. Not a highly available system. If you want to build a highly available system, it is going to cost more, but it'll pay for itself in the long term. So I did a talk day before yesterday about MemDS, which is an internal component in DynamoDB. We engineered it with this kind of concept in mind. Assume that all the caches are cold, because someday the caches will be cold and you will thank yourself for it. Your customers will thank you for it because your system stays up. So engineering for high availability is about thinking about these things up front and paying the price because it's worth it. So let me give you another similar kind of example. DynamoDB has request routers. Your requests come to a request router, which is then sent to a storage node where your data is stored, and so on and so forth. And like all of you, we use AWS services. Whenever a new kind of hardware comes along, we like to use it because it's more efficient. The scale at which we operate, we can save money, we can do good things for the planet. And we tested a new piece of hardware, and we found that at about 9,000 RPS, this request router was able to provide good latency. Standard. Drive higher RPS through the request router, utilization goes up, latency goes worse. That's the red line, we can't cross it, so 9,000 RPS is where it is. Everybody okay with this idea? Yes? Okay. So the question now is this. In standard operation, what would you engineer this request router to deal with? The first thing you should think about then is, what can fail? Okay, DynamoDB is a regional service. We want to engineer for a single AZ failure. Okay, that entire AZ was out. We did software deployment, or there was a networking issue, one AZ is gone. DynamoDB should continue to run just fine. The way in which we go about speccing the host is we say, when a complete availability zone went away, the entire load will put the fleet of request routers in their normal environment. If 9,000 was the limit, you cannot rate a host more than 6,000. We continuously add hosts to our request router fleet, assuming that a single AZ may go out at any point in time. What's the advantage to us from this? You know how often we deploy software to request routers? Continuously. At any point in time, somewhere in the world, there's hundreds of request routers which are getting the latest version of software. They just go down, their caches get cold, they come back up, they keep running. That's how you engineer for high availability. All right. Are we good so far? Quick show of hands, makes sense? All right. Rule number 2. When you build complicated systems, do not build them from complicated, or don't build them as complicated monoliths. Build them from simple parts. The reason for this is simple parts have simple failure modes. Use the same parts in many places, fix an issue with that part in one place, goodness all along. You have one complicated monolith, it's got really peculiar failure modes. You can build this complicated looking car from these pieces. Here's an architecture, a simple block diagram of DynamoDB. We literally built each of these as a microservice. Within each of these microservices, there are subservices. This gives us lots of advantages. Leaving all the technical stuff aside, Amazon has this concept of a 2-pizza team. A team which can be fed on 2 pizzas. Now, Conway's law says that your org structure and your architecture diagram are going to resemble each other over time. If you build things as small microservices, you have the advantage that each and every one of these do their own thing. The request router team says, I expose a contract to you. You can make this API call. I will serve this API call. I will do it in this amount of time. The streams team says the same thing. Each of these components expose an API. They provide a contract. And they're independent failure domains. They're not a monolithic system. Each one is managed by its own team. We build them all as independent systems, which are independently going through continuous deployment. So here's an example. I got storage nodes, I got request routers. We store data on your storage nodes. We store 3 copies of every item. Request routers are mostly stateless. We do deployments all the time. As long as you do a deployment in one AZ at a time, it's perfectly safe, because there's 2 other AZs which always are running. You want to deploy to request routers? Go ahead, do it. You can take an entire availability zone down. You wouldn't notice it. Engineer for high availability by thinking about these kinds of things. And in the long term, you will have a system which is much more stable, 0 downtime. Now, you can't just say, I wrote a bunch of code and I'm going to deploy it to a storage node on hundreds of thousands of hosts. So we spend a lot of time going through the normal things which a software engineering team does. An engineer does some development. They test it in a sandbox. When they're done with the sandbox and they commit it, it goes to a 1-box environment, which is a smaller environment of DynamoDB, mostly for testing. Larger and larger clusters. Alpha, gamma, zeta. We run non-production workloads or non-critical workloads on our zeta cluster. At any point, if there's a problem, if there's a regression in latency, if we notice the memory utilization went up, if we notice the number of file descriptors started to go up over time, all right, roll it right back, figure out what happened. A thing which is probably good as a practice in your engineering organizations is build the practice which says, at any point if you have a problem, roll back. The reason you do that is because when you operate at scale, if it can fail, it will. Someday, you will be in production and you will have a failure. If that's the first time you're thinking about how you roll back, it's not going to be a good day. Continuously plan on, if it doesn't work, roll back. That should be the first reaction. And if you engineer your system with scale, and you engineer it with enough microservices and isolation, a component which got a deployment and a rollback, US customers would not notice it. Your customers should not notice it. Okay. The third thing, since we're doing continuous deployments, it's really important that you do these deployments in a compatible way. It is pointless if you deploy code and you have tight dependencies between versions on the client and the server and all this stuff. We took a very, very conscious decision to say the SDK affords a very thin client. There's customers of ours who do not use the SDK who talk to the native API. You can do everything with the native API that you can do through the SDK, but this client is a thin client. The reason is, when you operate at scale, in how many hosts do you think this client has to be deployed? Tens of thousands. We have clients who deploy to hundreds of thousands of hosts. If we say that you need to update all your clients in lockstep, that's going to be horrible. If you need new functionality, update to the new SDK. If you don't need new functionality, don't update the SDK. No. Security fixes, things like that means it's a good habit for you to periodically update your SDK. But when you engineer that system, engineer it in such a way that you don't need to do lockstep upgrades to all of your clients at the same time. Do progressive deployments. Deploy it to 0.5% of your hosts. See if it works. Then deploy it to 1% of your hosts. Then 5, move it forward that way. But always do it in such a way that you can accommodate progressive deployments. Okay. We launched this feature called Warm Throughput November this year, 2 weeks ago. What does the feature do? It allows you as a customer to say, I have a table or an index. How many reads per second or writes per second can that table or index do? We spent about 6 months doing the development for this. We deployed the entire thing. We now have several hundred customers using it. It was completely transparent to customers who did not use this feature. Customers who didn't need warm throughput, doesn't matter. Customers who needed it, all they had to do was update the SDK. And we spent a lot of time engineering it, and here's how we did it. First, there's the client, there's the SDK, and between the client and the server, there's a data model for the exchange. Now, that's a reverse compatible or backward compatible data model. All the feature implementation is over here. Several weeks before the feature was deployed, we started looking at every table and every index in DynamoDB and figuring out what the warm throughput was. We built the job which would say, what is the warm throughput of your table? And we started populating metadata. This happened several months ago. We've got hundreds of thousands of tables, millions of tables, 34 regions worth. We populated the metadata. Now there's a pipeline which continuously keeps that metadata up to date. Great. Now that that worked, the next thing we did was we deployed code to the request routers which understood the new API. But we deployed it disabled. If, for some reason, you figured out that there's this feature coming down the road and you made a describe table call with a warm throughput, or you made an update table call with a warm throughput, the request router would say, sorry, I don't know. How did we do the deployment? We deployed it one AZ at a time. The code is disabled. No problem. Nobody can use it. Okay? Hundreds of thousands of request routers now have the new code. We started testing it. We enabled some internal accounts. We started testing it. Everything's good. We checked a couple of tables of ours. Warm throughput looked OK. We made sure that CloudFormation was able to use it properly, because the first thing people are going to use is CloudFormation with DynamoDB. We enabled that account. Everything's OK. What do? We do the announcement. Flip the bit. The code is now enabled. Hundreds of thousands of request routers now can accept the new request. The code's already there. Did the press release, pushed out the SDK, and within a few hours, we had the first customers making use of it. Total amount of downtime because of this, 0. The customers who wanted to use it were able to use it. The customers who didn't update their SDK, that's fine. But the SDK was pushed to the console. The console is also a user of the SDK. The moment we flipped the bit and enabled it, if you refresh the console, you saw a warm throughput. Total downtime, 0. All right. So I talked about deploying in parallel. It is important to deploy safely. Now, I mentioned that you have 3 copies of your data. There's 1 in every AZ. At scale, if something can fail, it will. At this point in time, what time is it now? 5:10 p.m. on Wednesday evening. Worldwide, there are some 100 storage nodes which are either being software deployed or had a failure or something. They're not good. There's some number of partitions on there. Those partitions only have 2 copies, 1 in each of the other 2 AZs. Would it be safe to deploy software to this storage node? No, you'd be left only with 1 copy. So as we're rolling through our software deployments, we go and check every single replica on that storage node. We go to the other AZs and say, are you redundant? If you're redundant, then we will deploy. If you're not redundant, we will not. We'll make a list of this storage nodes which are not deployed to, and we'll come back and clean up after that. All of this is automated. The other thing which we've learned in the last 13 years, there are some things which you should never do by hand. This entire process of software deployment is automated. If you can make it automated and make it happen continuously, it's better for your systems as well. That's one of the things we've learned. So we've talked at this point about the availability part of it. But the reason why customers come to DynamoDB, in addition to the fact that it's always available, is that we give you predictable latency, predictable performance at any scale. And let me talk about a couple of things which we've done in order to make that possible. So Joe talked about this earlier. Applications at scale do the same things over and over and over again, right? Think about your applications. When you operate at scale, does your shopping cart suddenly decide it wants to do something else, like searching for something? No. Shopping carts do shopping cart things. Search does search things. They do the same things over and over again. The other thing which I want you to think about is this. Human beings will tolerate latency, but they will find inconsistent performance to be intolerable. They demand consistency. My flight from Boston to here is a 6-hour flight. Nobody complains about the fact that it's a 6-hour flight. It's 5 minutes late, oh God, the whole world is going to come to an end, right? They will tolerate latency, but they demand consistency. And I'm sure your customers are the same way. They will search for things on your website many times over. Sometimes the search takes 3 seconds, 2 seconds. But if it consistently takes the same amount of time, they will tolerate it. But if it takes 3 seconds one time, 10 seconds the next time, yeah, they're going to be really annoyed about it. So your customers demand applications which give you predictable latency. Our customers, Amazon customers, demand the same thing. Therefore, your database needs to give you predictable latency as well. So a thing we spend a lot of our time on is making sure that we give you predictable latency. In addition to making for a better customer experience, it makes it much, much easier for you to engineer your systems. So we spend a lot of time building predictability, and let me tell you about some of the things we do, because those may help you as well. If you think about predictability and consistency as 2 axes, and these are orthogonal, you always want to be predictable at any scale. I speak with customers who are starting to use DynamoDB. It's a new thing, NoSQL. We were doing something else, relational database. It's not scaling. We're going to do a benchmark. And we're concerned that our benchmark is not going to be at our real scale. So we're going to test at 1 million RPS. Great, they tested 1 million RPS. And they're very happy about it. They go into production. They're now running at 5 million RPS, and they're happy. They've launched it. And the first thing they tell us is, you know what? At 5 million RPS, the latency is exactly the same. Predictable latency at any scale is something we value a lot. And just like you have to engineer for high availability, you have to think about that in your application. There are places in our code where we literally count. We use flame graphs. We look at elapsed time in code. And we literally see how much time is spent in each part of the code. And we spend a lot of time eliminating variance. If your code is going to do very, very different things in different scenarios, it's not going to have predictable latency. So we try to make sure that it always does the same thing and takes the same amount of time about it. So let me give you an example. DynamoDB has hosts in many AZs. So let's assume you have a client application up here. It happens to be in AZ1. You resolve the regional endpoint for DynamoDB in that region. Let's assume we terminate you, or terminate your connection, with a request router in AZ3. And you make a consistent read request. Well, or in this particular case, you're doing a write request, and the leader happens to be in AZ2. In order for us to do this right, your client in AZ1 talks to AZ3, which talks to a leader which happens to be in AZ2, which needs to guarantee the data goes to one other AZ. I've gone across AZ boundaries so many times I can't count. The leader could be in another AZ, like here. Now what happens? Completely different number of traversals on the inter-AZ boundary, no predictable latency. So we spent a lot of time. We built these 2 features last year. And we said, we will look at your client and where your client is coming from. And we will attempt to connect you to a request router in the same AZ wherever possible. And when you make a request, if it's an eventually consistent read, wherever possible, we will get the request served in the same AZ. Total number of AZ traversals, 0. Predictable latency for your requests. Do the same thing. Don't keep going across the AZ boundary if you don't have to. Now, I did say, do it where possible. When it's not possible, if you attempt to do a write and the leader is in another AZ, or you do a strongly consistent read and it's another AZ, we will have to do a traversal. Where possible, do the same thing over and over again. And this takes some thought, some engineering, which you'll have to get your developers to think this way. Another kind of thing, the applications we're talking about do the same things over and over and over again. It's simple for me to write SQL, which looks like this. Select these 3 fields from this table where something or the other, right? If you do this with a relational database, the first thing is you're going to read English, understand English, try to figure out what to do with this English, look at some statistics, try to optimize it. You're doing the same thing over and over again. And we said, try to do the same thing over and over again. What's the one word up there? Statistics. Statistics itself means variability. If you want predictable latency, here's the plan. Execute it. 1 step, done. This is the difference between a declarative and an imperative model. We chose this model for a reason. Another example, we implemented transactions in DynamoDB. In a relational database, you can do transactions by saying begin, some statement, another statement, so on and so on and so on. They're independent statements. You can intersperse reads and writes. In DynamoDB, in a transaction, the entire transaction is in the API call. How many of you have been in a situation where you're debugging a problem which appears to hang for some reason in the middle of a transaction, and you debug and you find that somebody else started a transaction and decided to go and get coffee? Cannot happen in DynamoDB because the entire thing is right there. Do the same thing over and over, but do it in the same length of time. So we consciously said we will implement single-shot transactions because we want predictable latency. And the last, I think, of these rules is, wherever possible, divide and conquer and use parallelism in your favor. So we have hundreds of tables over 200 terabytes. Let's assume we store the 200 terabyte table as a single partition, and we have to recover it. Okay. Fault isolation says that's going to be really horrible. But if I were to chop it into small pieces, which are 10 gigabytes, by the way, whether your table happens to be 200 terabytes or whatever, 16 times 10, 160 gigabytes, and we can do all these things in parallel, heal time is the same. And the heal time is the time to heal 10 gigabytes. Divide and conquer. But you have to think about these things at the point when you're engineering your application, because you cannot bolt these things on later. And when we have new engineers join the team, we start by telling them these things. If you have applications, oh, this one was definitely added for Vegas. Many customers want predictable, low latency. We find a lot of customers who attempt to do this by adjusting timeouts. This is dangerous, and I'll tell you why it's dangerous. What we've found internally is if you have a client which is making requests to a distributed service, each independent server will have a response time characteristic which looks like a normal distribution. If you want predictable low latency, hedge your request. Send the request to 2 servers at the same time. If one of the requests happens to be on the bad end of the latency curve, well, statistically, the other one's on the low end. Take the first response, keep moving. This is not an Amazon invention. This is a paper which came out of Google many, many years ago. There's a QR code there. So let me give you an example of that. The same client server with the cache. You want to serve 2 billion RPS, you got a 99% cache hit rate, you got a distributed database. How are you going to size that database if you're going to serve 2 billion RPS? The way we would do it, and the way we've internally done it, is that database will serve 4 billion RPS. Because not only is it going to hedge, it's going to run at constant work, which was the first part we talked about. So if DynamoDB is serving hundreds of millions of requests a second, our internal MemDS database is serving twice that at predictable low latencies. MemDS does it in tens of microseconds. If you want to engineer for high availability and low latency, this is how you have to teach your engineers to think, and this is how we do it. I said adjusting timeouts is dangerous, and here's the reason. This is a simulation with data from an actual engagement with some customers, and we tested it internally. I removed the latency numbers on the x-axis because the actual numbers don't matter. Customer did some testing of their application, and it appears that we, Amazon, advised them to use a lower latency. They chose a latency which was this red line here. System worked fine, worked for a long time. So we did this simulation, and we said, OK, here's a histogram of the latencies. We computed the Gaussian model on this. These are the two curves. It's a trimodal distribution. Great. A very small amount of time they got timeouts. One day, something happened in the network. This was the latency their application saw. What does that mean? Their application largely went into outage. Changing the timeout is a dangerous way to try and improve your latency, improve your response times. Hedge, it's much safer. So these are some of the things which we've kind of learned. Let me quickly run through these. Humans will tolerate latency, but they will absolutely demand that you're consistent. If something can fail, it is going to fail. Prepare for it. Build simple systems from simple pieces used over and over again. Build them with the idea that you're going to be doing backwards compatible stuff. Build it in such a way that you can do continuous deployments. Build it in such a way that you can use parallelism to your benefit. At the end of the day, what we want to do is we want to build boring systems. Okay? The reason this might sound odd. How many of you, when you build stuff and you use DynamoDB, would you like to say, option one, we decided to put our data on DynamoDB, and ever since it's been exciting and enthralling, and my pager's going off every single day? I don't think many of you. What we want is this. This is an actual customer quote. We put our data on DynamoDB, and it is boring. Build it so your applications are not going to keep you up at night. It's worth the time. So with that, I'm going to hand it back to Joe. Thank you, Joe.
Appreciate it. I think you can all see why Amrit is fun to work with. All right, so let's do a quick recap. We talked about some of the aspects of DynamoDB. I hope you have a much better idea for some of the principles that we use and we talk about. And we really balance out a lot of these concepts of what we can do for customers and how we should really reason over what capabilities we build next. I want to run you through a couple of things that we've done this year. If you didn't see it, it's a really big deal for us, is we cut on-demand prices this about 3 weeks ago by 50%. One of the things that our engineers do on our teams that you don't get to see is we're continually optimizing our system, and we get to the point where we can actually pass those savings back to our customers. Don't do it a lot, it doesn't happen all the time, but this is a case in which we were really excited to make DynamoDB on demand, which we really want it to be the default option for you. It's a lot less work for you, for customers. It's a lot easier to use with warm throughput. You now have a much more transparency on what that table is capable of doing. You now have an API to be able to scale your table, to increase more. This is a really big deal. We're really excited to pass that on. Same thing with global tables. We reduced the premium on global tables. There used to be a premium when you wrote across regions with DynamoDB. Now regional write is the same as a replicated write. There's no premium, same cost. We had a big year this year on security. We had quite a few launches. Resource-based policies are really helpful to be able to control access for a particular table. You can attach a policy to a table. Private link support. We just GA'd attribute-based access control as well. So just kind of increasing the amount of, I would say, integrations into the entire AWS system. And as Matt announced yesterday, we added strong, multi-region strong consistency to global tables. Previously, global tables has been around for a while. Used to be eventual consistent replication. We now have, asynchronous replication. We now have synchronous replication, which allows you to be able to achieve recovery point objectives of 0 for applications using strong consistency, and also be able to do strongly consistent reads across AWS regions with Dynamo. Some other good stuff. In addition to warm throughput and the price cut, we also introduced a capability this year to be able to specify a maximum throughput for an on-demand table. Really good for dev test. I would tell you I get many tickets of people that actually had a ticket or a test workload that went awry, spiked costs, and we kind of go through this dance. But being able to cap throughput either for your customers or yourself on an on-demand table is a good cost-saving exercise. It can be really helpful depending on the scenario. DynamoDB now has 3 0 ETL integrations. We've had OpenSearch and Redshift, and now we just launched a 0 ETL integration with S3, and a bunch of other good stuff. One of the things we really love is when our customers talk about what their experience is building on DynamoDB. Here's a number of sessions this year from customers like Duolingo, JP Morgan, Hermes, Roblox, customers from different industries building different applications on DynamoDB. These will all be up on YouTube. Highly recommend that you check them out. Again, we really like to learn from our customers. If you want more talks from the DynamoDB service team, the ones with dates on them are still in the future, so there may be availability left. The ones that have YouTube next to it, we'll find those on the internet. And because a lot of our talk related about architectural concepts with DynamoDB, here's some related content as well on some of the white papers, some of the previous talks that we've done on the DynamoDB team to talk about some of the different aspects of DynamoDB and some of the things that will supplement some of the things that you learned today as well. And with that, we just really want to sincerely thank you for choosing to come spend an hour with us. We hope you have a wonderful reInvent. If anybody has any questions, Amrit and I will be over in the corner there if anybody wants to chat. Thank you so much.